Welcome to lecture 6, part 4. This is the final part. So now we're going to combine the last two ideas where we both have a condition and a probability. So the idea here is that students go to the barista with 60% probability and self-service with 40%, unless the barista line is longer than 5 customers, and then all of them go to the self-service counter. Okay, so that's sort of one example of how you could combine these two ideas. So again, I guess before I go on, I should state that I am assuming that you have indeed been following along using the Nimitz model, and so you've modified the Nimitz model to have the probability or the condition in your current thing. Perhaps you have both. You could have both with separate models using the new model feature of Simio. If you have questions about that or want to know how to do that, let me know. I'm happy to show you. Okay, so in order to do this, we're going to use actually both ideas. We're going to use both the weight and we're going to use the condition response that we had before. And what we're going to do is we're going to say, look, and this is going to look a little tricky, I think, but it actually isn't as bad as you think. For the branching probability to the cell service, we're just going to keep it at 0.4. So you might think, well, don't we have to change that depending on the condition? But you don't. And the way to think about it is that if this weight is 0, then all the customers go down that branch, because that's the only thing with actual weight. It would have a probability of 1 because it would be 0.4 divided by 0.4. Remember, the way that Simio works is it adds the weights up on in all possibilities. That's the denominator. The numerator is the weight on each line. So the weight there would be 0.4. The numerator would be 0.4. The denominator would be 0.4, and all of the customers would go down that branch. Now, we'll multiply this 0.6 by the barista Q less than or equal to 5. And by doing that, if the barista Q is less than or equal to 5, then suddenly this gets a weight of 0.6. If it's greater than 5, it'll get a weight of 0. And that all comes to what we need. Okay, so to do this, again, you start from this. If you started from the default settings, it would be 1 or 1. Maybe your default settings looks different because you're starting from the previous parts of the lecture. And what we'll have, I think that one of the key sort of syntax errors people make is when we do this multiplication. Remember, computers don't understand that as multiplication unless their language set has that in it. Most language sets don't. Most language sets use an asterisk for multiply. So I think that's one of the more common syntax errors made with multiplications is that when you program is that you have to remember that to use an asterisk. But once you do that, then you have it. This is going to be 1. Remember, this will be 1 if the Q length is less than or equal to 5, 0 otherwise. And that's exactly what we want. And so just to see how that would work, if there were 4 customers in queue, the connector 5 here, it would go, the connector 5 will have a weight of 0.4, connector 2 will have a weight of 0.6, and so that'll be the relative probabilities. It would be the same thing if there was 5 in queue. And then the tricky thing to keep in mind is if there were 6 in queue, the connector 5 would have a weight of 0.4, connector 2 would have a weight of 0, so every customer arriving or leaving the cashier would go to connector 5. If you run this, I don't, as opposed to the previous slides, I don't have the results, but if you run this, the results, and I hope this isn't surprising to you at this point, it's going to show roughly 40% self-service. And that's because it's very rare. It's a rare event in our simulation with the settings we have for there to be more than 5 customers in the queue. So it actually validates what you would expect to